For my honors students, there are a couple things additional things I want you to know. If you're not an honor student, you can stop. You also need to be able to draw Lewis dot structures for polyatomic ions, not just molecules, but polyatomic ions. So there's an extra step when you're dealing with an ion. When you're adding up the total number of valence electrons, you need to add 1 for each negative charge on the ion. And then you're going to subtract 1 for each positive charge you have on the ion. So you're going to modify your total number of valence electrons based off of the charge of the ion. You're going to place brackets around the ion and label the charge in the top right-hand corner when you're done drawing your ion to indicate that your ion has a charge. So let's look at an example of this. The perchlorate ion. Perchlorate, when we count up the electrons, 1 chlorine has 7 valence electrons. 4 oxygens each has 6 valence electrons, so that's a total of 24. So that would be a total of 31 valence electrons, but we're going to add 1 more electron because this ion has a negative charge. So really we're going to place 32 electrons. Chlorine goes in the middle. The oxygens go around the outside. We're going to draw the minimum number of covalent bonds we need to connect everybody together. When we do that, that uses up 8 of the electrons, so we have 24 electrons left to place. And no double bonds are needed because 24 electrons is the right number to put on all the oxygens in order to give all the oxygens a full valence shell. Chlorine already had a full valence shell with its 2, 4, 6, 8 electrons around it. And the final step is to put brackets around the ion and then indicate the charge outside of the brackets in the top right corner. Let's look at the ammonium ion. Nitrogen has 5 valence electrons. Each hydrogen has 4 valence electrons. I'm sorry, each of the 4 hydrogens has 1 valence electron for a total of 4 valence electrons. So we've got 9 electrons total to place, except because this ion has a charge of +1, it must have lost an electron somewhere, so we subtract that 1 electron. We're going to place 8 electrons in this Lewis dot structure. Nitrogen goes in the middle because it's the singleton atom, also because hydrogen can never go in the middle. We connect everything with the minimum number of covalent bonds needed to join the atoms. When I do that, that is 1, 2, 3, 4, 5, 6, 7, 8 electrons. I have drawn all the electrons that I have available to me. And that's fine because every atom shown here either has the full octet, in the case of nitrogen, or I don't expect it to have a full octet. In the case of hydrogen, hydrogen is happy with just its 1, 2 electrons. Therefore, my Lewis dot structure is complete once I put square brackets around the structure and indicate the charge in the top right corner. You may have noticed a few slides ago, let me go back, on this sulfur trioxide slide, you may have wondered, why did I draw the double bond to this oxygen? What if I had drawn the double bond to this oxygen instead? That would have been a totally valid structure, so long as I updated the other lone pairs to accommodate it, like this. So this now has 3 lone pairs of electrons, and this one only has 2 because it has 2 covalent bonds coming to it. Or it would have been equally valid for me to have put the double bond over here to this oxygen. I have 3 equally valid ways to draw this Lewis dot structure. When we have a molecule that can't be correctly represented by a single Lewis dot diagram, then we use resonance structures. The actual structure is going to be an average of all the possibilities that we show. And you show that we have these multiple possibilities by using a double-headed arrow between the different structures. So for instance, for the ozone molecule, whose formula is O3, 3 atoms of ozone bonded together, we can have a central oxygen with a double bond to the left or a central oxygen with a double bond to the right. These are equally valid structures, and we show that they're both equally valid by showing a double-headed arrow between the two structures. This is the sulfur trioxide example that we discussed on the previous page. That double bond could equally well be placed between the sulfur and this right-hand oxygen, the sulfur and the left-hand oxygen, or the sulfur and the top oxygen. These are all equally valid structures, so we use a double-headed arrow between the structures in order to represent that resonance. I hope this helped.